Okay, so let's start with chapter 18. Now, in chapter 18, there's only a few things that you need to know. First is Ohm's law, right? Which is actually very simple. It's not something that's unfamiliar to you all. Now, second thing, we actually want to talk about resistance as a unit on its own. Okay, so before we start on Ohm's law, let me talk on the easier one, which is actually resistance. Okay, so as we know, if I have a circuit here, okay, I have a resistor here. Let's say this is 6 volt and this is 2 ampere. By now you should know that V equals to IR. Okay, so with that I actually can find the resistance of this resistor, right? So R equals to V over I, which is actually 3 ohm. So this is 3 ohm. Okay, so now what happens, what actually, right, causes this thing to have 3 ohm? Okay, it could be the wiring inside, it could be actually the material that this uh, resistor uses, okay, when it's manufactured. Okay, so talking about material, we then realize that different material have different level of conductivity or resistivity. Okay, so insulator generally have higher resistivity. Okay, so we have this thing called resistivity. It is a property of element itself. Okay, so generally insulator, they have high resistivity. Okay, so high, while conductor, they actually have low resistivity. Okay, in other words, the conductivity is high. Okay, because if your resistance is low, you actually can conduct electricity easier, right? Okay, so it is easier for you to conduct electricity. Okay, so now over here, what I want to introduce to you all is actually a formula, and it goes like this: R equals to rho L over A. Okay, now resistivity is denoted with the Greek alphabet rho. Okay, so this rho here is resistivity. This L here is length, and this A here is the cross-sectional area. Using our base SI unit, cross-sectional area will be meter square, L will be meter, okay, R will be ohm. Okay, so this R is actually our resistance. Okay, so please don't mix resistance with resistivity. Okay, so let's take a look at this formula. R equals to rho L over A, and with a diagram we try and figure out what it actually means. Okay, so rho L over A, rho is a constant. Okay, so for now let's just use the same metal, okay, copper. So we are going to talk about copper wire. Okay, so different copper wire of different length or different cross-sectional area, but they are basically the same element, and therefore resistivity is constant. Okay, so let's not focus on resistivity too much. Let's just focus on length and cross-sectional area. Okay, so over here I have two wires. Okay, so I have a thin wire. This is a thin wire, and I have a thick wire, right? Okay, so you do know that when current flows, it's actually not one current doing the job, right? But we now know that it's a domino effect. So actually I have like a lot of electrons flowing through it. Okay, now I have a thick wire. In other words, my cross-sectional area here, okay, wires are cylindrical in shape. Okay, so my cross-sectional area here, this region here, my A, we call this A2. Okay, and we compare it with this, we call it A1. Now it is very obvious that A1 is lesser than A2. Okay, so this is what we can figure out first. Okay, now we can keep another thing constant. We can treat this wire as a 3-meter long wire, and we also treat this wire as a 3-meter long wire. Now I want you to compare A1 and A2, and you realize that A2 is actually larger. Now what it means is that I actually don't squeeze as much. Okay, so imagine I have, say, just 6 electrons. Okay, now these 6 electrons, in order to enter the thin wire, they actually need to be packed in this manner. Okay, so maybe 2 electrons per section. Whereas if I want 6 electrons here, you realize that they actually can be packed in this manner. In fact, I can have 6 electrons flowing in one section, and very easily you see, right, for just comparing one section, okay, on the wire, you realize that the green part, for the thick wire, you actually have in that section you actually have more electrons than the thin one. Okay, so what it means is that the resistance of a thick wire is actually lesser than the resistance of a thin wire. Okay, we are assuming two things here. Now, of the same length and of the same resistivity. Okay, because we are assuming that it's copper wire, right? Okay, so we are assuming two things here. Okay, so basically you realize that the area actually plays a part. Okay, so thick wires, they have lesser resistance than thin wires. Okay, so the larger your area, because you are allowing more electrons to flow through in one section, your resistance actually decreases. Okay, so this is number one about area. Okay, so this is about area. Right, we're going to go to the next part where we actually talk about length, and then we will combine these two concepts together. Okay, so the next part is about length, which I won't speak at length. Okay, so now assume that I have two wires, and right now they are of the same cross-sectional area. Okay, one is this long and the other one is this long. Okay, so maybe one is 1 meter long, and even though it doesn't look like it, this can be 2 meter long, and they are made of the same material. Okay, same cross-sectional area. So just make a quick remark that in this case A1 is equals to A2, and of course this A1 and this A2. Okay, the difference is the length. So how does length play a part? If you read this equation right, R equals to rho L over A, so ignore all other factors because they are constant. Just compare R and L. So when L increases, R should increase. Okay, so over here they have a directly proportionate relationship. So when length increases, R increases. So you may ask yourself why. So I want you to think of it as though in this case you are running 2.4 km versus maybe you are running just a 100-meter dasher. Okay, which will you be more willing to do, right? So obviously you're going to be more willing to give it your all for the 100-meter. Okay, the 2.4 is a bit far. Okay, your resistance goes up. Okay, so think of it that way. So the electrons actually have to travel further in a longer wire. Okay, that's why the resistance goes up. Okay, whereas in a 100-meter sprint, the electrons have shorter to go, so their resistance is naturally lower. Okay, if electrons have further to go, they actually got more obstacle to pass through. Okay, and that's one of the reasons why the resistance actually increases. Okay, so for length, you do realize that this relationship exists. Okay, so this relationship is something that we can conclude here, whereas for area wise we realize that the relationship is inverse. Okay, so this is directly proportionate, and this is inversely proportionate. Okay, so one thing to know about A is that area is actually equals to pi r squared in this case. Okay, so let's see how that plays into part. Okay, so let's come up with a very simple question. So I have a wire X and Y made of copper. Okay, so they are both made of copper. So wire X and Y made of copper. Okay, so first scenario is that X equals to Y, rather length of X equals to length of Y, which is equals to 2 meter. Okay, so you don't need to know, but the thing is that the cross-sectional area of X is equals to 2 times the cross-sectional area of Y. Okay, so AX is bigger, 2 times. Okay, so in that sense, if R of Y equals to 5 ohm, find R of X. Okay, so we can draw the diagram. So basically AX will look something like this. So this is AX, and this is actually AY, right? Okay, so remember we say that resistance in area and resistance, they are like inversely proportionate. Okay, so since AX equals to 2AY is a factor of 2, so Rx will be equals to 5 over 2 equals to 2.5 ohm. Sorry, I realized the SI unit here is wrong, so this should be 5 ohm. Okay, so yeah, then we have this. Okay, so Rx equal to 5 over 2, which is actually 2.5 ohm. Okay, now scenario number 2, what if my area is the same, so Ax equals to Ay, but my length is different, so that I have Lx equals to 2Ly. So if Ry equals to 5 ohm, find Rx. Okay, so this is another scenario. I'll use another ink to draw the wires. Okay, so first I have the same area. Okay, but one is longer. So Lx equals to 2 of Ly. So maybe this is Ly, and then this will be Lx. Okay, so remember that they share a direct proportional relationship. So what happens is that since Lx equals to 2Ly, so the factor difference is 2, so Rx will be equals to Ry, which is 5 times 2. Okay, so 5 times 2, which is 10 ohm. Okay, so now the last scenario that I want to talk about is actually with regards to radius. Okay, so let's say that Lx equals to Ly, okay, which is equal to 2 meter if you need a number. Okay, but however Rx is equals to 2Ry. Okay, so if Ry equals to 5 ohm, find Rx. Okay, now what needs to happen here is that we actually need to figure out the area ratio. Okay, so Rx equals to Ry. Okay, so if that's the case, now pi Rx square, which is the area. So what we want to find is Ax, right? So Ax equals to pi Rx square. It's actually equals to pi 4Ry square. Okay, so 2 times 2Ry, the whole thing square, right? You get 4Ry square, which is actually 4 pi Ry square. And clearly, Ay should be equals to pi Ry square. Okay, so you realize the area is 4 times a factor of 4. Okay, now since then with this we actually go back to our first working here. Okay, so the area is actually 4 times difference. So if Ry equals to 5 ohm, Rx will be equals to, because it's 4 times larger, so we divide by 4, so 5 over 4, which is 1.25 ohm. Okay, so this is actually my Rx. Okay, so I'll just stop the introduction to wire resistance here.